Welcome everyone. In this video, we're going to be unpacking a slightly older Trojan. Our focus here though is on continuing to get comfortable using the Ghidra tool in order to do that. You're also going to see some complications that will arise when using Ghidra, particularly the decompiler, when we encounter malware that does some non-conventional instructions, or at least the ways in which it's using them, that can throw off the process of disassembly and decompiling. In addition to that, we'll analyze a little bit of shellcode in order to fully unpack the sample. We'll also use x32dbg or x64dbg in order to extract the unpacked sample from memory. So you can see here the source of the sample came from a malwaretrafficanalysis.net posting from a few years ago. As I said, this is a slightly older example. We can start by analyzing this Trojan using PE Studio, and we're not going to get into all of the different techniques and ways in which we can detect packing, but with this sample we can look at some of the more obvious, at least some of the more obvious ones that I use, and see or at least suspect right off the bat that it is likely packed. With PE Studio, we don't have any particular signatures. PE Studio does have a signature system that you can find. If you open up the PE Studio folder, you'll see some XML files in there, and it would match if it was able to recognize based off of those signatures a well-known packer, and in this case it doesn't. Other things then that we look for, or at least things that I look for, the sections are certainly one, and something that stands out with these, as PE Studio has identified some of the characteristics of these that stand out, as well as the names themselves, is that we have several very non-standardly named sections. Not a particular, a sole indicator, but certainly something that is suspicious. If you look at the entropy, there is a relatively low entropy across this entire file, but that just might be simply the way in which the malware is packed. We can also then look at libraries, very few imports. That is oftentimes an indicator that you're dealing with something that is packed, is that it has very few imports because we're just looking at the unpacking code. With the libraries, of course, then it would go kind of hand in hand that we have very few imports as well. We can also look at the strings, and in doing so, you'll see that while we have a very long list of strings, most of them are more or less nonsensical, and that the number of recognizable strings are very few. So again, another fairly strong indication that this is in fact a packed sample. So now let's turn our attention to using Ghidra in order to do some more in-depth manual investigation here. There, of course, may be other tools available that could allow you to extract the PE file dynamically, but I wanted to use this as an opportunity to continue to build some hands-on experience with Ghidra. Once you open Ghidra, you'll have to create a project. I'm just going to call this Simda because that was the name given to this particular Trojan, and add our executable to the project folder. From there, we can open up with the code browser, and if you have not analyzed it, then of course this will be the time in order to do that. For this demonstration, I'm going to go with the default, and this will then just take a little bit here as it begins performing the program analysis. Another indication that I will use in order to help me determine if something is packed or not is oftentimes to look at that program once it's been disassembled or decompiled and see the amount of functions that have been identified. For this sample, there are very few functions. So that when taken in context of all the other indicators that we talked about is, again, lends to a very strong possibility that we're dealing with a packed sample. Now, we can start by analyzing the entry point. And we don't necessarily want to spend our time looking and tracing through all of this functionality. There are some clear Windows API calls, such as load cursor and create file. There's some other custom functions that might take some time to analyze. One technique that works for me on a regular basis is just to look at how these functions end, right? If we're tracing unpacking functionality, then what we're trying to do is really trace essentially a one-way flow to where it gets to the point where execution is passed to that unpacked, whatever that unpacked sample happens to be. So looking at how the functions end, that is one technique that I have found that I can use in order to trace this one-way flow. Now, if we scroll down in this function, we can go to where the return is, and we can see in the corresponding window, the listing window, that it does something a bit non-standard. What that is that it pushes an address onto the stack before it returns, right? And clicking on the return here in the decompile window, we're in sync. That shows that we're at this first ret. So what Ghidra has done is it has identified this as a function. Now, if you look a little bit closer, you'll see that what it's pushing onto the stack is actually the address for the instruction after the ret. So 40139A is this location right here. So this is what I meant at the beginning of the video when I say that it's doing some very unconventional, it has a very unconventional way of returning. So what's actually happening then is this function is continuing to this location, in which then it pushes another address, which happens to be for the next instruction after this ret. Before it does it one more time, it now pushes this location onto the stack, and that location, 40138A6, happens to be located right here. Now, the results of this particular technique is not only that the function gets cut off a little prematurely because of all this very non-standard activity, but also that this code doesn't get disassembled. So now what we can do is we can highlight this location, and you can either right-click and select disassemble, or you could just hit the D key, and now that will disassemble that code. This becomes either its own function because of the way that it's been broken apart, or something that we could also do is we could go back and highlight all of these instructions here, and we could just edit them out. One way to do that would be to use the bytes view. So if you look under Windows, there's bytes. That will open up this window here, and you'll notice that much like all of the windows in Ghidra, they stay in sync. So as we've selected all of these push rets, we can see those also located over in this particular hex view. In order to modify these bytes, essentially patch this binary, then what we need to do is we need to first select all of the instructions that we want to clear, and then right-click and we can clear code bytes or use the C key as a shortcut. That will clear the disassembly there, and essentially it unlocks that so that we can go ahead and modify that here in our hex view or our bytes view. We can then also select this little icon up above. That'll enable us to edit, and now we can begin overwriting those bytes. So in the case that I just want to knock them out, I can just go ahead and do hex 90s until we've reached the end of that or that last return. Now once we're done, we can lock this view again if we want to, but we've now knocked those out. And what that provides us with the ability to do is to actually see this function in its entirety. In order to do that, you can select Clear Flow and Repair. And now what we should see here is that we have that entire function. So what we were missing before. So if we skip to the end of this function, then we can look at this ret. Now, keep in mind, ret takes whatever value is on top of the stack and moves it into EIP. That's the location that the CPU will go to. So with this function, it's pushing a value, EAX, onto the stack very close to when it's returning, which is, again, very, very non-standard. It's very similar to the technique that we saw previously. This is not going to the next location, though. If you look at the value of EAX, and Ghidra displays that value to the side here, it's the address 401130, we could also highlight EAX, and we'll see that a few instructions above, there is a move into EAX, which is that address. This means that we can double click on that address to go to that location to investigate this function as well. Now, this one continues in a very similar pattern, in that if you look at where it returns, we have a return instruction. Right before that, we have a jump to that location, and immediately before that, we have a push ECX. So we need to know or understand what the value of ECX is. You'll notice here that you don't get the value annotated to the side. And if we scroll up, you'll see a move into ECX, and it's the data at this location. Double-clicking that reveals that that's undefined. So what this means is that this value is populated during runtime. A very common technique when you're working through the unpacking process is that you'll see some of the initial code allocating memory that it will then place shellcode into, and that will become the unpacking logic. So that's likely what we're seeing here. In order to continue our analysis then, we could try to figure out by looking back at some of the previous logic what this value will be, or what's likely the easier thing to do is we can set a breakpoint here and just stop execution at this point to investigate what is in this global variable, or if we want to break a little bit later on to see what's in ECX. That way we can then trace execution into the shellcode. In order to do that, I'm going to go ahead and we're going to switch over to x62dbg and set a breakpoint at this address, 401156. Okay, I have the Trojan loaded up in the debugger, and we're about to set the breakpoint. The breakpoint is now set, and we should be able to begin execution. You'll see that x32dbg breaks at main, which we're not necessarily interested in, so we'll resume execution once more, and now we encounter our breakpoint. We can see this as the instruction here at the top of our window. This allows us now to look at the register ECX, and we'll see that ECX contains the address 5D6ED0. So let's go ahead and we'll step from the jump to the push, to the jump, and now to the ret. The next thing we have to decide is how much time we want to spend analyzing the shellcode. Again, in this case, I'm just interested in getting to the end. I want to get to the unpacked binary. So I'm not particularly interested in understanding all of the details for this particular unpacking technique. So what we can do then is we can extract the shellcode from memory, we can disassemble it, decompile it, and see if we can follow that one-way flow that I've been discussing through this video. So one way to get that shellcode out of memory is to use the save data command. This command takes 3 arguments. You need the name of the file that you want to save. You need the base of the allocation, where in memory you want to begin saving from, and then the size, how many bytes you want to save. So what we need to figure out first is where is the base of this allocation, and then how large is it. So we can actually use the memory map tab for that. And because we were in that region of memory already, it's highlighted right here. You can also tell that this is the base of the allocation because this is the first lower address that matches the address that we're currently at. That means that the base of our allocation is 550000 and it has a size of 87000. Okay, now we know the base of the allocation and the size, so we can use that information in order to extract this content from memory. So with the save data command, we provide the path and the name that we want to save this memory content to, in this case shellcode, using commas to separate, the base of the allocation, and then the size. And as you can see, once you hit enter, you should get a message here saying that the content was successfully written. If you get anything wrong or if there's any errors, you'll also see that down below here. Let's now switch back to Ghidra. We'll go to our project view. I'll get this out of the way, as I will get this out of the way. And we'll add the shellcode. Here we can see it on our desktop to our project. Now, this is shellcode. It's raw binary content. So because it lacks a file format, Ghidra cannot detect that for us. So we need to filter and find the format ourselves. In this case, it's 32-bit shellcode for Windows. So I'm going to grab this option, and now we're ready to import. Remember, this is just importing that shellcode into our project. We haven't actually done the analysis yet. Instead of dropping this onto the code browser, I'm going to go back to the window that I already have open, and I'm going to open it up in this project. That will keep things, in my opinion, a bit more organized here. This has not been analyzed, so we need to go ahead and perform the analysis. And what we also need to do, because we're looking at shellcode, there is no way for Ghidra to determine what the entry point is. So we need to go to that entry point and make sure that disassembly has started there. To do that, we just need to find the raw offset for the shellcode. We actually already know that. If you go back to the CPU view, we're at an address of 5D6ED0. Our base allocation is 55000. So we need to just simply subtract the current location actually subtract the base allocation from the current location. And that will give us the raw offset, so 86ED0. Now with that information, we can go back to Ghidra. We can hit G, that will bring up the dialog for go to, and we can just type in 86ED0, and that will take us to that offset. Here you can see that it was able to identify this as a function and the disassembly has already been performed. So again, I'm going to take a very similar approach to what I've previously discussed. And instead of trying to analyze this code, I'm just going to look at how it returns. This function follows a very similar pattern that we've now seen throughout this entire unpacking process, in that before we have our return instruction, we're pushing onto the stack EDX. And this, again, does not follow the normal process of a function using a prologue and an epilogue in order to return to where it was called. So we could try to analyze what EDX is. We can see a few instructions above, there's a move into EDX, some local variable, or because we're already running in the debugger, we could just set another breakpoint and see where this function returns. So I'm going to set a breakpoint at an offset of FC3. Go back to WinDebug, clear our previous command, and now we'll set a breakpoint at 5D6 FC3. And now we can resume execution. We're at the instruction push EDX, which means that EDX contains the value that we're interested in. We can see that EDX is currently 402037. Now, what's interesting about this is that this is taking us back to one of the addresses in the original address space of when our binary was executed. So this could indicate that the unpacking process is actually complete. Let's go ahead and we'll follow that ret back to 402037. Let's compare. At this location right now, we have an opcode of 55 or a push EBP. Push EBP followed by move EBP. ESP is more of a standard function prologue. Let's look at that location though in our original binary. We can use the G key to quickly jump to that location, 402037, and right now we have completely different bytes. Not that they weren't disassembled or decompiled, but that they're completely different. So that's a pretty good indication that our unpacking process is complete. In order to now extract that, we can use x62dbg and use the Scylla or Scylla, I still don't know how to pronounce it, plugin. We're at the current entry point, right? So if this is in fact our unpacked executable, this is now the entry point, 402037. That's already been defined, and we can use the IAT auto search and get imports. And what that hopefully has done for us is it's identified the imports for this unpacked executable so that when we dump it from memory, we're able to analyze the code and actually see those imports. The next thing we can do is we can use the dump command to save this to the desktop. And I've done that no, I didn't. I deleted those. I do find on occasion that I need to do a fixed dump. So take the dumped binary and open that with fixed dump. And you'll see that that has now created a demo simda dump scy.exe. Now we're done with Scylla, and what we can do is add our dumped executable to our project. So let's add that here. It's a PE file, so it's able to be identified. There's our summary information, and now we can go back to our main code browser and open that file and analyze it. All right, as that's analyzing, you can immediately see a fairly significant difference. We have a large number of functions and other areas we could investigate, such as looking at strings. You'd also see that we have a large number of identifiable strings. We can also look at the imports, and that's very helpful that we know not only did we get the unpacked sample, but using our tool, we were able to fix that import table. If you skip that step, then these would all be broken, and it would look like this actually has 0 imports, and it would make it a little bit more difficult to trace these Windows API calls. If we want to look at one as an example, and I know this just because I spent a little bit of time a while back analyzing this binary, it has some additional anti-analysis in that it looks at the processes running on the system and, I guess we're not done analyzing, and it looks for basically a list of known processes that it does not, analysis processes that it wants to avoid. So if it finds things like Wireshark, then it's going to change its behavior. So in order to get a process list, one of the ways to do that, at least one of the ways I'm aware of, is to use under kernel 32, create tool help 32 snapshot. And we can see that there are 3 cross-references listed to that function. So it's been called 3 times. I know it's the last one. Looking at this last one, you can look at the decompiled results. And you have now all of these imports clearly identified here. We have the call to create tool help 32 snapshot. Process 32 first is used to get a pointer to the first process object. And then process 32 next allows us to iterate that. If you combine that, the fact that we're getting a process and then doing a comparison, that's a pretty good indication that it's trying to look at or identify potentially bad processes from the malware perspective. So it's comparing this string 1 to this local 11C. If we look at string 1, it appears that it already has the name of an executable as part of its label. So we can double click on that and we'll find that it does in fact have cv.exe as its value. And if we continue to scroll down, we'll find additional process names: iris.exe, wireshark.exe, and others. Now that we have the sample unpacked, we can continue to analyze the program, discovering other anti-analysis techniques, as well as, and more importantly, being able to figure out exactly what it's up to. I hope you enjoyed this video, and getting hands-on with Ghidra, I'll continue to produce these. So subscribe to my channel so you know when the next video is available.